It turns out that using a determinant, the determinant of the 3 by 3 matrix, I can figure out whether 3 points on the xy plane are on the same line. If 3 points are on the same line, we say that those points are collinear. So let's make a quick sketch here. Here are 3 points that are on the same line, or at least they appear to be. And let's call these points x0, y0, x1, y1, and x2, y2. It turns out that if I set up a matrix with x0, y0, x1, y1, that's supposed to be 0 there, and x2, y2, with, as a third column, all ones, the determinant of this matrix will tell me whether or not these 3 points are on the same line. If the determinant is 0, they are. If the determinant is not, they are not. So I'll do an example in a minute with some specific numbers, but for right now, let's find the determinant of this matrix. Let's call it A. And we want to find the determinant of A. And if that determinant is 0, then we can say, yes, these 3 points are on the same line. What does this determinant look like? Well, it's going to be row 1, column 1, times the determinant of the remaining entry. So that's going to be y1 times 1 minus y2 times 1. The second entry gets subtracted. So I'm going to have y0 as my leading value there. And then I'm going to have, I'll grab a different color here, a matrix made up of these values. I take the determinant of that matrix and I get x1 times 1 minus x2 times 1. And then I'm going to add to that 1, that's row 1, column 3, times the determinant of this matrix. That will be x1, y2 minus x2, y1. And then I'll distribute these. I'm going to get x0, y1 minus x0, y2 minus x1, y0 plus x2, y0 plus x1, y2 minus, let's see if I can move this over. There we go. x1, y2 minus x2, y1. Let's put those in a different order. I'm going to rearrange these so that the x0 terms come first. So they're actually already in that order. And then the positive x1 term is x1, y2 minus the other x1 term, that's x1, y0. The positive x2 term is x2, y0. And then I have minus x2, y1. And I've done that so that I can factor out first the x1, first the x0, leaving me with y1 minus y2. Then I can factor out from the next two terms the x1, and then I can factor the x2 out of the last two terms. Now I want to talk about all the different ways in which this expression can equal 0. One of the ways that that could happen is if all of the x values were 0. So let's assume that x0, x1, and x2 were all 0. If that were the case, then I'd have 3 points whose x-coordinate was 0. And that means that I have 0 something else, and 0 something else again. And of course, those 3 points are going to be collinear because they're all on the y-axis. Another way that this expression could add up to 0 is if all 3 of these expressions were 0. So if that were true, then I would have y1 is equal to y2, y2 is equal to y0, and y0 is equal to y1. If y1 is equal to y2 and y2 is equal to y0, then that means y1 is equal to y0. Well, I already have that here as well. In other words, y1 is equal to y2 is equal to y0. They're all the same number. Oops. All three of those are the same number. And if that's the case, then I'm going to have 3 points whose x-coordinates might be anything. We'll just call them A, B, and C for now. And the y-coordinate could be anything. Let's call it K. But if it is, whatever it is, it's the same for all 3 points. And that means I'm going to have AK, BK, and let's even go negative CK. And those points are also collinear because they're all the same distance from the x-axis. All I've done so far is rewrite the expression that makes up the determinant. This is the determinant of our matrix. I've done some algebra, I did some distribution to get it into this form. I reordered the terms to get it into this form, and then I factored the terms to get it into this form. So all I've done is rearrange the terms in a variety of different ways. I'm going to rearrange them one more time. I'm going to write them, let's see, kind of going to take this line, and I'm going to write the positive terms on the first row and the negative terms on the second row. So I'm going to have something like this. So I'll have x1 here, x2 here. My positive x1 goes with y2, my negative x1 goes with y0, my positive x2 goes with y0, y0, and my negative x2 goes with y1. And what I really want is to add these up and for the result to be 0. And I've shown you a couple of trivial ways in which that can happen, but what's interesting about thinking about them in this particular arrangement is I could have, for example, let's see, I can have this term be equal to 3 and this term be equal to 5, so I'd have 3 minus 5 here, and if this term were 5 and this term were 3, then I have 3 minus 5 and 5 minus 3, I'd get 0. Now that's with only 2 of the terms in each line. The third one in that, I'm just making up an example here. So for my third pair of terms, let's say that each of them is 0. One of them is 6 and the other is negative 6. So they add up to 0 as well. I can find individual specific numerical values that when all 6 of these terms are added together get me 0. And what we call that is a linear combination. Now we're not used to working with quite so many terms when we do that, but that is essentially what's happening here. So if I can find a linear combination of these terms where the sum of all of those terms is 0, then what I've found is that the points whose values made up this equation, or this expression rather, right? These values here are arranged in a particular way here. Those points are collinear. So let's do an example. Okay, here I have 3 points, and I want to know if they are all on the same line. I want to know if these 3 points are collinear. So I'm going to write a matrix. The first point, the second point, and the third point. It's my first 2 columns, and all ones as my third column. I'll call that matrix B, and I want to know what the determinant of B is. And that's going to be 3 times the determinant of these 4 values, which is 2 minus negative 4. Then I subtract the next one. My second leading number is 0 times the determinant of the matrix made up of these 4 values. And actually it doesn't really matter what that is because my leading factor there is 0, but I'll just write it anyway. I have 5 times 1 minus 1 times negative 1. Then I add the third term, and that's going to be 1 times, I have 5 times negative 4, that's negative 20, minus 2 times negative 1, which is negative 2. So here I've got 3 times 6 plus 0 plus 1 times negative 20 plus 2, which is negative 18. And that is 18 minus 18, which is 0. So these 3 points are collinear. One of the ways that this is working, one of the things that's happening here is that we're looking at effectively the slopes of the lines that go through these 3 points. This point, this point, this point. Here is one of the, let's see if we recognize this is 2 minus negative 4. 2 minus negative 4. That's the y value in one point minus the y value in the other. 5 minus negative 1 is 5 minus negative 1. That's the x value in one minus the x value in another. And the third one is, let's see here, 20 minus negative 2. That doesn't appear here, but it comes from the second and third points here, 5 times negative 4 and 2 times negative 1. So there's something weird going on here, but the other two, I don't know what to call, they're factors. I don't have them in factored or in the form of a numerical factor yet. I haven't done the arithmetic. Let me take a highlighter and highlight this, and that is my 2 minus negative 4. That's the difference in y values. And I'll highlight this. That's the difference in my x values. And so it appears as though I might be able to use this same determinant to find the equation of a line, because this is, let me get the right pen here. This is my y, sorry, that is my x2 minus x1, and this is my y2 minus y1. So that's my slope. My slope is embedded in these two terms. Slope is embedded into that, or maybe hidden in that in a way. So let's take this last weird combination that isn't really quite working out for us, make the observation that these two numbers are not being used in this computation here, and I'm going to change those into generic x and y values. So I'm going to take that 3, 0 out of there and replace it with x, y. And now everywhere I see a 3 here, I need to replace it with an x. And every place, I think I'll use a different color too, just so we can really see what's going on here. I'll use blue. I'll use x there. Everywhere I see a 0 from the original 2 points, I need to replace that with a y. Well, that's going to happen here as well. Here's a 0. I'll replace that with an x. Here is a 3. I will replace that with a y. And remember that this term here, these two values here came from multiplying the 5 and the negative 4 and the 2 and the negative 1. We didn't use these values at all for that. So there's nothing to replace. There's nothing to do with that. And now what I'm going to do is off to the side here, having replaced those values, I'm going to go off to the side and I'm going to recompute those values, and I'm going to distribute the y and the x. So instead of 3 times 6, I'm going to have y times 6 instead of 0 times 5 plus 5 minus negative 1, that's also 6. I'm going to have x times 6. And then I'm going to have, let's see, I have plus this number here, and that is, that we said that was negative 18. So I have minus 18. But I still have a determinant here, don't I? I mean, I replaced, what did I replace? I replaced 3 with y and 0 with x, but I still have, throughout all of this, I still have the computation of a determinant, and we've already established that the determinant in this case was equal to 0. So I'm going to say this equals 0, and I'm going to rewrite this in a more familiar form. I'm going to say for now 6y minus 6x minus 18 equals 0, and then I'll add the non-y terms to both sides. I get 6x plus 18. Divide through by 6 and you get y equals x plus 3. And that is the equation of the line through these 3 points. Well, through these 2 points. We took one of them out, but we know they're collinear because the 3 points are collinear because we found the determinant was 0 before we started this process. So once you know the determinant is 0, you can recompute the determinant and actually find the equation of the line that those 3 points are on. And here's the really cool thing. Any 2 points are collinear. And so since this point up here is generic, so the first example we did, we found the determinant of the matrix where these 2 points, these 2 values were numerical values. And then the second time through here, we've replaced those specific values with generic variables, right? But since any 2 points are collinear, it doesn't matter if the determinant is 0 at this point, right? This matrix here, in fact, let me rewrite one. Let's call it M, matrix M, nice generic matrix M. If I have a point x1, y1, oh gosh, let's try that again. x1, y1, and x2, y2, and a generic x, y, and I add 1s in those positions, the determinant of that matrix will give me the equation of the line, right? Because these are generic. The equation of the line through this point and this point is given by the determinant of this matrix.